So hi guys, in this lesson we'll solve the second part of the question we started off in the previous lesson. This will enable us to better understand the calculations involved in quantitative analysis. The question we started in the previous lesson is stated as follows. 0.25 mole per dm cube of hydrochloric acid was titrated against 25 milliliters of a solution containing 6.5 grams of hydrated sodium trioxocarbonate 4 in 200 milliliters of solution. Question 1. Find the number of moles of water of crystallization in the base. Let's start off with this question. Now, we're told that the titration was against sodium trioxocarbonate 4 hydrated. That is, sodium trioxocarbonate 4 containing water of crystallization. But because we do not know the number of moles of water of crystallization, we have represented it as X. And this question basically tells us to find the number of moles, that is, find the value of X. Now, to do this, we must remember that we can only obtain the value of X if we know the molar mass of this base. From the molar mass of the compound, we can extrapolate the value of X. Now, the formula to obtain molar mass we know is molar concentration equals mass concentration over molar mass. So since we know the molar concentration already to be 0.115 mole per dm cubed and the mass concentration to be 32.5 grams per dm cubed, we can obtain the molar mass. Let's plug in these values into this formula. We'll have that 0.115 will be equal to the mass concentration, which is 32.5, over the molar mass, which we can represent it as M. To obtain the value of M here, we cross multiply. This gives us that 0.115 times M will be equal to 32.5. To obtain the value of M, we divide both sides by 0.115. And this gives us the molar mass of the hydrated salt to be, let's do that quickly, 32.5 divided by 0.115, 282.6. So we have the molar mass of the base to be 282.6 grams per mole. Now, that's not the end. We still have to find the value of X. To obtain the value of X, all we have to do is to remember that the molar mass of a substance is the sum of the atomic masses of all the individual elements that make up that substance. So if we sum up the atomic masses of all of these elements, we should be able to find the value of X. Let's do that quickly. Now, we know that the atomic mass of sodium is 23, but since there are 2 atoms of sodium, that becomes 23 times 2 plus carbon is 12 plus oxygen is 16. But since there are 3 atoms of oxygen, it becomes 16 times 3 plus X times, we've already been given the molar mass of water to be 18. And this is equal to 282.6 grams per mole. When we simplify this, we have 46 plus 12 plus 48 plus 18x equals 282.6. When we sum up these first 3, we obtain 106 plus 18x equals 282.6. So we'll take 106 over to the other side to obtain the value of X. And that gives us 18x to be equal to 282.6 minus 106. When we subtract this, we should get 176.6. So we'll have that 18x is equal to 176.6. Of course, to obtain the value of X, we now have to divide both sides by 18. On dividing by 18, we obtain our value for X to be 9.81. So X is equal to 9.81, which is approximately 10 moles. So there are 10 moles of water of crystallization in the base. Let's move on to the second question. The second question asks us to find the volume of carbon dioxide gas evolved at standard temperature and pressure. Now, we have a balanced equation of this reaction. We can see that at the end of the reaction, carbon dioxide gas is evolved. We've been asked to find the volume of this gas evolved. To do that, we must first find the number of moles of carbon dioxide produced or evolved. And to find the number of moles of carbon dioxide gas produced, we have to first find the number of moles of sodium trioxocarbonate 4 decahydrate that took part in this chemical reaction. Now, to do that, watch and follow. We first have to note that in the reaction, we had a molar concentration of the base to be 0.115 mole per dm cube. What that tells us is that the base contains 0.115 moles in 1 dm cube, which is the same as 1000 cm cube of solution. So the base contains 0.115 moles in 1000 cm cube of solution. But of course, we're not given 1000 cm cube of solution. We're only supplied 25 cm cube. So now we have to find the number of moles of the base in 25 cm cube and not in 1000 cm cube. So we'll say X moles of the base will be in 25 cm cubed. To obtain the value of X here, we cross multiply, and this gives us X times 1000 equals 25 times 0.115. When we divide both sides by 1000, we obtain the value of X to be, let's do that here, 25 times 0.115 divided by 1000. This gives us X to be 0.002875 mole of Na2CO3.10H2O. Now what this means is that it is 0.002875 moles of this base that has taken part in this chemical reaction. Now that's not all. You can see that 1 mole of the base produced 1 mole of carbon dioxide gas. What this means is that 0.002875 moles of this base will produce the same amount of carbon dioxide gas. So the number of moles of carbon dioxide gas produced will be 0.002875 moles of CO2. It is with this value that we will now find the volume of the gas evolved at standard temperature and pressure. Stay with me. So, to do that, we'll have to remember that 1 mole of every gas occupies a volume of 22.4 dm cubed at standard temperature and pressure. So, since we have 0.002875 moles of the gas, we'll find out the volume that will be occupied by this number of moles of the gas. What we have to do is to cross multiply this, and we'll have the volume X times 1 to be equal to 0.002875 times 22.4. When we quickly press this with our calculator, we obtain 0.0644 dm cubed. So the volume of the gas evolved at standard temperature and pressure is 0.0644 dm cubed. Or you can convert to cm cubed by multiplying by 1000, and that gives us 64.4 cm cubed. So this is the volume of carbon dioxide gas evolved at standard temperature and pressure. And that's all for this lesson. I'd love to see you in the next one.